Hey Brand Bombers, it's Miss Morel, and today we are kicking off section 7.2, so the second section out of 4 sections in this chapter. So today's objective is just to talk about the different structures of ionic compounds and talk about the strength of the bonds, and then to be able to categorize them as exothermic or endothermic. So a review vocabulary is a compound, and this is just a combination of 2 different elements. We learned that in one of the very first chapters. So if you combine 2 different elements, that is a compound. We'll have some new vocabulary, and then the main idea is oppositely charged ions, so a positive and a negative, they attract to each other to form electrically neutral ionic compounds. So an ionic bond, what is this? That is electrostatic force that holds oppositely charged particles in an ionic compound. So I like to think of it when we look at our periodic table, something from the left side and the right side being bonded together. So we have a metal and a non-metal. That's something you'll see on your final exam. And it's something really important for you to know and understand that an ionic bond is a metal and a non-metal. So compounds that contain ionic bonds are metals and nonmetals. They are called ionic compounds, as I just said. So binary ionic compounds contain only 2 different elements. So a metallic cation, so a positive, and a non-metallic anion, something like a gas. And binary, hopefully you can remember, bi means 2. So whenever we hear the prefix bi, we know we're talking about 2 of something. So if we are talking about this, it contains 2 different types of elements. So when we talk about this, something like formation of sodium chloride, we have sodium, which is on the left side of our periodic table, right here. We have chlorine, which is on the right side of our periodic table. And we can see that sodium has a +1 charge and chlorine has a -1 charge. So +1, -1, when we add those together, we come up with a net charge of 0. So that works perfectly how they bond together. And sodium chloride is just regular table salt that you and I eat. So different properties, so positive and negative ions, they exist in a ratio determined by the number of electrons transferred. And so we will look more at that in the next section, but there's always a repeating pattern of the particle packing. So you can see here, we can see this crystal structure, and we'll be looking more at crystals as we continue throughout the book. But right as we approach Christmas time, we'll actually be making a kind of fun borax crystal lattice Christmas ornament for your chemistry. I know it's kind of corny, but hopefully you can smile about it. And so hopefully you'll enjoy making that, and just know that you'll be looking at some amazing crystals when we look at that. So the strong attractions among the positive and negative ions, they result in the formation of a crystal lattice. And so a crystal lattice is a 3-dimensional geometric arrangement of particles and is responsible for the structure of many minerals. So if you shake out some of your salt shaker and you look at the shape of your salt, you'll see that that is a crystal shape. So the melting and boiling and hardness, they depend on the strength of attraction. So we can see here, we can see how the melting point of things that are ionic compounds, how it's very, very high. So 660 degrees Celsius is really quite hot, and boiling point is really, really hot. So it's really difficult to melt different salts. It's something that you and I cannot do with our regular oven, that sort of thing. So in a solid, ions are packed into position and electrons cannot flow freely. Solid ions are poor conductors of electricity. And so if you take your salt shaker and you shake it out and then you try to conduct electricity with it, you'll find that it's not a very good conductor. And we'll probably be doing a lab to test that sort of thing. Liquid ions, or ions in an aqueous solution, have electrons, and they're able to move freely, and so they conduct electricity really easily. So if you take that same salt that does not conduct electricity when it's just on the table, but now you put it in water, you'll be able to see that it can hold an electrical charge and that can flow through it. So an ion that in an aqueous solution that conducts electricity is called an electrolyte. So yes, that's the same thing that you see in your Gatorade that you're drinking. And so an electrolyte, that is just things that help our body to make different connections and to be able to function properly. All right, so here we can demonstrate how and why crystals break when the external force is applied. So we can see how here we have in the first picture this crystal lattice, but we can see how when we tap it with a hammer, how it would just easily slide down and it would break that bond. So reactions that absorb energy, these are called endothermic. So, and then energy, when it's released energy, this is exothermic. So if they are cold because they're absorbing the energy, that would make them endothermic. And if they're releasing, that means they get hot, that they're letting the energy go, and you and I can feel that heat. All right, so the energy required to separate 1 mole of ions in an ionic compound is referred to as lattice energy. So if we're going to separate that, that's lattice energy. So lattice energy is directly related to the size of the ions that are bonded. And so the smaller the ions of the compound, the more closely spaced the ionic charges, and it requires more energy to separate. Electrostatic force of attraction is inversely related to the distance between the opposite charges. So the smaller the ion, the greater the attraction. All right, the value of a lattice energy is also affected by the charge of an ion. So here we can take a look at this, and we can see how the lattice energy, how it increases dramatically as we move down this table. All right, one quick question for you all. So why are solid ionic compounds poor conductors of electricity? And the answer is that they are electrons that cannot flow freely. So if you put them in water, then they're able to flow. All right, you guys are awesome. Thank you for watching and have a really awesome day. Bye, you all.
What's fish tank for?
That's Sam. He's my little boy. He says hi.